We now want to discuss some of the representations of the Lorentz-Lie algebra that we have been looking at recently. The first example is the one of a unique spin S. Unique spin representations are constructed from the realization that the spin S starts with the Casimir operator B0 and then goes to B0 plus 1, B0 plus 2, B0 plus 3, until finally it gets to the magnitude of B1 minus 1. Now this magnitude of B1 actually comes from the fact that this is B1 squared. Now obviously if this series is going to result in a unique spin, then since the spin starts at B0 and goes up to B1 minus 1, then if B1 is equal to B0 plus 1, B1, where B1 is a real positive number, then the series will result in the fact that you only have one spin S, where S is the value B0. Now for that I emphasize that B1, you recall, can be any complex number, and B1 here must be real, and it can be positive or negative such that its magnitude minus 1 is equal to B0. This then results in a unique spin. If we return then to the formulas that we had for the coefficients CS, then we'll see that all of the CS vanish for all S, and therefore the Lorentz operators Ri do not mix any of the spin values from one spin value to another one. Certainly an example of this is the spin for the representations for the electron, the proton, the neutron, and so forth. Which have a unique spin of 1/2 h bar. In fact, one wonders if all these different representations of the Lorentz group have any use or any value at all. And this is a rather complicated question, but one that we can certainly answer by saying that some of these mixed spin representations are of great value. We want to look next at the case where B0 is equal to 0 and B1 is equal to 2. Immediately one can see that the spin is going to start out at the value 0 and continue to the value 1, which is the magnitude of 2 minus 1. So consequently, this will end up being a mixed spin representation where we have one Lorentz-Lie algebra representation consisting of spin 0 and spin 1 values. It turns out, kind of ironically, that this is the most important case that you can possibly have. There are exactly 4 basis vectors for S and sigma. Where S is equal to 0, sigma must also be equal to 0. But if S is equal to 1, then sigma can be equal to plus 1, 0, or minus 1. Obviously, the 0, 0 component is invariant under rotations, and the other 3 constitute a 3 vector. We actually have to take a linear combination of these two, of the spin plus 1 and spin minus 1, to get an x and a y coordinate, and this then becomes the z coordinate. Well, with a little bit of reflection, we realize that a 3-component vector under rotations added to a 1-component rotational scalar, all of which mix up under Lorentz transformations, gives the suggestion, which is true, that this object is a 4-vector k mu. You recall that k mu is in fact any kind of vector k mu has a 0th component, which is a scalar under rotations, like time is, or like the energy is, and then the other parts, ki, form a vector under rotations. So on the one hand, this is going to give us vectors such as the operators x mu and p mu, which are fundamental to the algebra itself, as well as our concepts of space, time, energy, momentum, and mass. So what we have concluded is that the vectors for position and for momenta are themselves these representations of vector representations, 4 vector representations, which are actually mixed spin representations. On the other hand, we get vectors such as A mu. This is the electromagnetic 4 potential, which is also a vector, and from which the electromagnetic fields are derived, F mu nu being this antisymmetric combination as we discussed earlier. The connection is actually deeper when we reflect on the fact that the inclusion of the electromagnetic field is achieved by the replacement of the momentum vector by the momentum vector minus E over c A mu, where A mu is the vector potential. This is often called the principle of minimal electromagnetic interaction. And if we perform this replacement of everywhere we have a P mu in our Hamiltonian or our Lagrangian, with P mu minus E over c A mu for a relativistic case, then it turns out that we will exactly incorporate the electromagnetic field in the correct way, assuming that the electromagnetic field potentials can be created from this vector. So what do we conclude from this? Well, we would begin by thinking of particles and think, oh, these representations that are unique spin representations are going to encompass all of the important particles. And therefore these mixed spin representations are not important. And now we see that the first, or the simplest mixed spin representation we could imagine, B0 equals 0, B1 equals to 2, which consists both of spin 0 and spin 1, form the most important object we can imagine, namely a 4 vector under the Lorentz transformation, or the Lorentz-Lie algebra. And that encompasses, of course, 4 momenta, 4 position, all of their associated concepts, and the 4 potential itself, which gives us the electromagnetic field. Let's talk a little bit more about this representation where B0 is equal to 0 and B1 is equal to 2. The 4 potential A mu could represent a particle with a mass 0 or a particle with a mass greater than 0, either one. A mu could be interpreted in the quantum theory, it turns out, as a wave function for a photon when the mass is set equal to 0. Now this sounds kind of unusual, but it's actually correct. The interpretation is very complex because of the behavior of the photon and the behavior of its spin, and the fact that the wave function A mu is actually a real function. The 4 potential is a real function. Takes us back a little bit when we start thinking about, could this be a wave function in the sense of quantum theory? Because we're used to thinking of a wave function psi in quantum theory as being a complex function where psi star psi gives us the probability. And that's always positive definite, and it's normalized to 1. Here we have something very complicated, and it requires a great deal of work to properly interpret. That's because A mu not only has an invariant form, A mu, which of course is not positive definite, but also because of the concept of spin involved with a photon. The photon has 2 states of spin, and of course the electromagnetic potential here represents 4 states of spin, and so we have to be very careful when we look at that. One could go a little bit further there and say, well, we know that we have P mu is equal to m squared c squared as an operator equation. And if we're going to have a massless, a particle that has no mass, it follows that P mu acting upon anything gives us 0. Well, in the position representation, you recall that P mu acting backwards on the y gives us minus I, where the units where h bar is equal to 1, I times partial mu y. And the partial mu here is g mu nu partial with respect to x nu, summed over nu. Thus it follows that if we look at P mu acting on A, which has to give us 0, and we let this P mu act backwards in units where h bar is 1, the minus I times the minus I cancel and gives us a minus 1. And when we get a minus 1 here, we can cancel that because we get a 0 on the other side of the equation. The partial mu operator is called the D'Alembert, and we can write this A here projected as a wave function, projected on the position representation with the 4-vector mu. That's mu in the sense of the last equation that we wrote down, where mu goes 0, 0, and then 1, minus 1, 1, 0, 1, plus 1 for the 4 different states mu of associated spin. And therefore the electromagnetic field picks up that spin from this state right here, which we'll discuss in a few minutes in greater detail. This object here then becomes a mu of y0, y1, y2, and y3, in other words of x, y, z, and t. And this equation, where the 4 components for spin given by this equation have been combined linearly in order to form a 4-vector with this index mu. We'll pursue this later, but we note that in fact the equations del A mu equals 0 are the source-free equations of Maxwell. So this gives us Maxwell's equations, and we can see how this, how the wave function A, when projected onto position and the spin, actually gives us the 4-vector with a spin dependence. Now, granted, we have not gone through this in detail. This is just an overview, and this requires very careful consideration in order to make this an interpretation that works. One of the best references that I know of for this is actually in the book by Schwaber, Quantum Theory of Fields. There are 2 other things that we have to be very careful about with the representations of the Lorentz algebra. If you've been following this material by reading the book by Gelfand, Menlos, and Shapiro, and the other book by Neymark, then you realize that there are actually 2 representations for these 2 values. One where B1 is the spin plus 1, say for a unique spin, and another representation where B1 is equal to minus S plus 1. This is called the conjugate representation. More specifically, in the text they refer to the conjugate representation as where either B0 or B1 changes into a negative value. And if either of those changes into the negative value but not both, that's called the conjugate representation. It turns out that if B0 is equal to 0, a representation is equal to its own conjugate. That's something that we'll have to discuss also in greater detail later. The interpretation of this in quantum theory, if B0 is equal to 0, or if B1 is equal to 0, is that the representation and the conjugate are the same. And it turns out that in that case, the associated field can be taken as a real function. And in quantum theory, this means that the particle is the same as its antiparticle, which, for example, is true of the photon. Now, on the second topic, it can be shown that the most general invariant form that can exist on these representations is given by the following, where G is the metric here, and G actually has the form of minus 1 to the s to the power s. If we think about that, that's quite a remarkable situation, because in fact this minus 1 to the s says that in mixed spin representations there is a metric G which alternates in each of the spin representations from positive to negative, as this power s minus 1 to the s, for as s goes 1, 2, 3, 4, 5, and so forth, each one of these has a different sign. As you're aware, the overall sign of the metric isn't important, but the relative sign of these components is important. In fact, it's from this simple origin that we are able to obtain for the mixed spin representation where B0 is equal to 0 and B1 is equal to 2. That's our 4-vector representation, like position, momenta, and so forth, that this minus 1 to the s gives us, in fact, this metric between the time component and the space component. Well, this is absolutely phenomenal. So, because what we have now done is shown that if we're going to have an invariant bilinear form that is supported on this space, then we must have a metric which is in exactly the metric which started everything in the first place. This was the metric for position and momenta, and then for the Lorentz transformation that followed from their antisymmetric products as angular momenta that actually gave us the Lorentz Lie algebra. And now we have come full circle to rederive that metric out of the system, but rederive it in a form that is much more general than the form that we originally had it. Originally, we had this invariant form as 1, minus 1, minus 1, minus 1 between the time and the space part of a 4 vector. Now we're saying for these mixed spin representations, the metric actually takes the form of alternating signs for each of the spins that one has included. Obviously, it follows then for a single spin that that one does not have that, or a unique spin that one does not have that sign oscillation back and forth between plus and minus, and one can take a definite sign. So we end up with this indefinite aspect to the metric as we move from one component, the time component, to the space part of any 4 vector or in any mixed spin representation as we go among the different spins. In a more complicated sense, these two concepts here, the concept of the invariant bilinear form and the concept of the conjugate representation, work together in a deeper way when we start looking at space and time inversions. And if we want to have a form that is invariant for the proper Lorentz Lie algebra, that is, in other words, under space inversions, then it turns out you always have to include the conjugate representation with the representation in order to form a bilinear form that is invariant for the whole system. I want to take a diversion for just a minute to talk about an interesting area called irreducible tensor operators. Now, we are all aware of the fact that when we look at the representation J and sigma of angular momenta, these irreducible representations are given under the action of J squared, Jz, and J plus and minus by these equations right here. We've studied that under our angular momenta. Now, if we want to write, and this should have been absent here, the state J sigma written as a creation operator, A dagger J sigma, acting upon the vacuum, and this is a new notion in the course at this point, we're going to imagine that out of the pure vacuum that this operator creates this state J and sigma. And if that's true, then it follows that of course, for a vacuum, J squared onto this, or Jz onto this, or J plus or minus onto this vacuum is going to give us absolutely 0, because the vacuum itself has no angular momenta. Consequently, we can write a very interesting set of equations. By first letting these act on the vacuum, we can see that J squared on the left side of J dagger gives us this equation right here. J squared onto A dagger onto the vacuum would give us this right here onto A dagger onto the vacuum. Likewise, Jz commutator with this gives us sigma times A dagger Jz. And finally, J plus or minus onto A dagger gives us this equation. Now, how can you see that very clearly? It's very easy. Just put the vacuum, a state 0, on the right-hand side of each of these commutators, and you'll see that you retrieve exactly this equation right here where A dagger hits it, and where J squared hits it first, you get a 0. So the second part of each of these commutators vanishes when it hits that state. And therefore we get the equations right up here that we had before. Now, kind of turning our back and saying, let's not look back at what has happened before, we can now say, here we have a set of operators, a dagger, that have certain well-defined commutation rules with all of the angular momenta operators. J squared, the Casimir operator, Jz, the maximum Cartan subalgebra, and J plus or minus, which are the E plus or minus operators for raising and lowering. We can say that any operator now, which has these commutation rules, is called an irreducible tensor operator. That's A dagger J and J sigma, is an irreducible tensor operator under O3. We can generalize this result, in fact, to hold for tensors for any Lie algebra that have the appropriate commutation rules. We can also take the dagger of all of these equations, and since J squared and Jz and J plus and minus are Hermitian or anti-Hermitian respectively, we then get associated commutation rules not for A dagger, but for the dagger of this, the transpose complex conjugate, which is in fact A itself, A of J and sigma. We can then set up commutation rules between A dagger and A exactly like we did for the harmonic oscillator, or like we would do for creation and annihilation operators in a second quantized theory, where these are the creation and annihilation operators for a given state. These, however, you notice are kind of unusual because we have created a state of cert J and sigma, but in fact there is no position or momenta associated with these, and that's not absolutely necessary. Right here we're creating states that simply have spin and its z component and do not have an associated energy, mass, momenta, position, time, and so forth like that. That is possible under the way that we're dealing with the Lorentz Lie algebra because we have separated out the intrinsic spin part from the XP Heisenberg algebra, which is totally separate from it.